Welcome back, dear learners, to today's Explainer. I am absolutely thrilled to guide you on a cosmic journey today. We're going to travel from the very familiar mechanics of our own solar system all the way out to the profound, mind-bending mysteries of galactic structure. Our universe began about 13.8 billion years ago from an extremely hot, dense state in what we call the Big Bang, and space itself has been expanding ever since. Today, we're going to zoom out, step by step, to understand exactly how this massive puzzle is pieced together.
Think about this for a second. What if everything we can actually see out there, every shining star, every glowing cloud of gas, every planet, is just a tiny fraction of what's actually holding it all together? It's a pretty wild thought, right? To find the invisible giants hiding in the dark, we first need to understand how the cosmos works on a much smaller, visible scale. Because once we understand the rules in our own backyard, we can easily spot when those rules seem to get broken out in the deep universe.
So here is our cosmic itinerary for today. We'll start with our local neighborhood, move on to the lives of stars, figure out measuring the cosmos, and finally tackle the dark matter mystery.
Let's kick things off with Section 1, our local neighborhood, its origins, and our sun.
Okay, let's dive into this by starting right at home. Before we can understand massive galaxies, we really need to understand the basic building blocks, stars and solar systems. It all starts with the nebular hypothesis. This is the widely accepted model that our solar system formed from a massive rotating cloud of primordial gas and dust. And we don't just guess this, we have incredible supporting evidence. For instance, we can actually observe protoplanetary disks of gas and dust forming around young stars in places like the Orion Nebula. Gravity pulls these clouds together, and we see that the planets in our solar system have near-circular coplanar orbits, meaning they all revolve on roughly the same flat plane, exactly as you'd predict from a spinning disk of material. Fun fact for you, over 99.8% of all that spinning mass ended up forming just the sun.
Right at the very center of that flattened disk formed our sun, the absolute powerhouse of our local system. The sun's interior is brilliantly structured into three main layers. It all begins deep in the core. Here, enormous pressure and heat cause hydrogen atoms to combine to form helium in a process called nuclear fusion. By the way, these are the exact same light elements whose abundance was predicted by the Big Bang Theory. This fusion creates a staggering amount of energy. That light and heat then pass through the middle layer, the radiation zone, where energy is transferred outward as electromagnetic radiation. Finally, it hits the convection zone, the outermost layer. Here, hot gases rise to the surface, cool down, and then sink back inward, creating these continuous looping currents that push heat to the sun's surface.
Moving on to Section 2, the lives of stars, from main sequence to supergiant.
So, that's our sun, but our sun is just one specific type of star. As we zoom out farther, we need to understand how different stars live and die across the universe. To make sense of the billions of stars out there, astronomers use an incredible tool called the Hertzsprung-Russell, or HR diagram. If you took a random sampling of stars from our galaxy and plotted them, you'd get this chart. It plots temperature against luminosity, which is just a fancy word for brightness. But be careful, it's a bit counterintuitive. The temperature scale actually goes from coolest on the right to hottest on the left. The luminosity scale goes from dimmest on the bottom to brightest at the top. The vast majority of stars, including our sun, fall right along a diagonal line stretching down from the upper left to the lower right. We call this diagonal line the main sequence.
Where a star sits on that diagram and exactly how long it lives completely depends on its mass. Higher mass stars burn through their fuel incredibly fast, staying on the main sequence for a much shorter time. Because of their immense pressure, they can fuse heavier and heavier elements all the way up to iron. Lower mass stars, on the other hand, burn slower and longer, only fusing elements up to carbon. But eventually, both types run out of hydrogen in their core, the fusion dies down, and they begin fusing helium, causing their outer layers to massively expand until they become massive red supergiants.
Which brings us to Section 3, measuring the cosmos. How far are we?
We now know how stars work and how they evolve. But to understand the structure of an entire galaxy, we need to map where these stars actually are. Which brings up a massive question. How do we know how far away these distant stars are? We can't exactly stretch a tape measure across expanding space. Well, for nearby stars, we use a brilliant geometric trick called parallax. As the Earth orbits the Sun, our vantage point changes. By measuring the tiny angle shift of a nearby star against the background of much more distant stars, we can use simple trigonometry to calculate its exact distance. Using this method, we can measure distances in parsecs, with 1 parsec equaling about 30 trillion kilometers. But parallax only works for stars that are relatively close to us. This parallax trick is just the first step in what astronomers call the cosmic distance ladder. We use the parallax method to accurately measure distances to nearby special stars called Cepheid variables. Because we know their true distance, we can figure out their true brightness, turning them into what we call standard candles. We then use these standard candles to calibrate our measurements for even brighter, more distant events, like Type 1a supernova. This incredible chain of measurements allows us to determine the distances to entirely different faint galaxies stretching across the cosmos.
And now for our final section, the dark matter mystery, galaxies and the unseen force.
Now that we have the tools to measure distances to distant galaxies, we have arrived at the climax of our explainer. Because when astronomers pointed their instruments at these distant galaxies, they found a massive, baffling discrepancy. First, they noticed that light from distant galaxies is shifted toward the red end of the spectrum. This is called redshift, and it proves that galaxies are actually moving away from us because space itself is expanding. In fact, we can calculate exactly how fast a galaxy is receding using Hubble's law, where velocity equals the Hubble constant times the distance. So if a galaxy is, say, 100 megaparsecs away, and we use a constant of 70, it's moving away at 7,000 kilometers per second. But beyond just galaxies moving away from us, we can also use this redshift to calculate the exact orbital velocity of individual stars within a galaxy.
And this is where things get really strange. According to Newtonian mechanics, galaxies should behave quite predictably. We assume that the more luminous a body is, the more light it emits, the more mass it contains. So most of a galaxy's mass should be concentrated right in its bright, dense center. Based on the Newtonian equation for expected velocity, the orbital speed of a star should decrease the further out it gets. Simply put, the further a star is from the dense galactic center, the slower it should be orbiting.
This curve brilliantly illustrates exactly what that math predicts. This is an expected rotation curve. You see the velocity sharply rise near the dense core and then steadily drop off the further out you go into the less dense, darker edges of the galaxy. This is what absolutely should happen based on all the visible, normal matter, the atoms, gas, dust, and stars that interact with light.
But here is the shocker. When astrophysicists actually measured the velocities in galaxies like Andromeda, the plotted graph deviated wildly from the prediction. Look at that flat line. The curve doesn't drop off at all. It stays completely flat as far out as we can measure. The stars at the very edges of the galaxy are whipping around incredibly fast. By all known laws of physics, these galaxies should be ripping themselves apart and flinging stars into the void. The only way the physics works to keep those fast-moving stars from flying off into deep space is if there is extra invisible mass exerting a massive gravitational pull.
So the crucial point is that visible, luminous matter simply isn't enough to explain galactic mechanics. And it's not just these rotation curves. We see extreme distortion of light behind galaxy clusters, a phenomenon called gravitational lensing, that can only be explained by way more mass than is visible. We also see it in the cosmic microwave background. The CMB is the faint leftover heat from about 380,000 years after the Big Bang, when electrons combined with nuclei so light could finally travel freely. When we look at the temperature deviations in this ancient light, it absolutely requires extra mass models to explain. All of this solidifies the theory that unobservable, invisible dark matter simply must exist.
Which leaves us with the ultimate cliffhanger for today. If everything we've learned over the last 13.8 billion years, the formation of our solar system, the fusion inside our sun, and the light from distant stars only represents a tiny fraction of the universe's actual mass, what exactly is this invisible dark matter that is holding our entire universe together? Research is ongoing, and the cosmos is waiting to be totally understood. Thank you so much for exploring the universe with me today in this explainer. Keep wondering and keep looking up.